Now I'm going to show you how to calculate the pH of an alkaline solution. So the example is, what is the pH of a 0.2 mole per decimeter cubed solution of sodium hydroxide, which would of course be aqueous. Well, although it says that on the label of the reagent bottle in the lab, there's no such thing as an NaOH entity in the solution. When you dissolve sodium hydroxide, which comes as solid pellets, in excess water, fully dissociates to give individual sodium ions and hydroxide ions. And these individual ions are coated, if you like, or hydrated by water molecules, which is what the AQ symbol designates. So inside your reagent bottle you have separate sodium ions and hydroxide ions. You do not have NaOH units, and certainly never, you should never say sodium hydroxide molecules, because this is ionic. So if we've got, if it says 0.2 moles per decimeter cubed of this, then for every one of those that we've put in as solid, we're going to get one of these. We're assuming it's a strong alkali in the sense that it will fully dissociate. So 0.2 moles per decimeter cubed of this one, and 0.2 moles decimeter cubed of this one. So if this is the sodium hydroxide, 0.2 moles of that in every decimeter cubed dissociates to give 0.2 moles of that and 0.2 moles of that. Okay. There are some alkalis that are poorly soluble in water, and then you cannot assume that the concentrations of the aqueous ions are anywhere near the concentration of the solid. So if you think about insoluble or poorly soluble group 2 hydroxides that you learn about in AS chemistry, you wouldn't be able to calculate making this assumption. But for strong alkalis, readily soluble, then this is the assumption that we make. This is what we're going to use now, the concentration of the hydroxide ion, because we can use the ionic product of water to calculate the concentration of H+. So we know that the Kw is the concentration of hydrogen ions multiplied by the concentration of hydroxide ions. And this is temperature dependent, but at 25 degrees C then it has a value of 1 times 10 to the minus 14 moles to the 2 dm to the minus 6. Okay. And so we write in the H plus here that we're looking for, because once we've got this one we can calculate the pH, and this is going to be multiplied by the concentration of OH minus, which we have here. So this is 0.2 moles em to the minus 3. So if I rearrange that, so all I'm going to do is move this one underneath here, and that gives me my expression for the H plus concentration. So if I write 1 times 10 to the minus 14 over 0.2 now, just to show those who are not comfortable about handling the units, instead of writing moles to the 2, I'm just going to write moles times moles, because that's what it means. The moles squared is that. And similarly, dm to the minus 6, it's going to be dm to the minus 3 times dm to the minus 3. The video on the origins of the ionic product of water, in there you'll see where these units come from. And doing it this way just enables you to see how easy it is to cancel down. One of those cancels with one of those, and one of those cancels with one of those. So the the numerical value of this, it's going to be 1/10 to the minus 14 divided by 0.2, so that's the same as times it by 5, so it's going to be 5 times 10 to the minus 14, and my units, I'm left with moles dm to the minus 3. So that's the concentration of H plus ions, not hydroxide ions. That's the concentration of H plus. So if I was doing it down here, you see, I would simply write 0.2 moles dm to the minus 3, and cancelling, I would simply cross that out and the 2 to leave moles on the top, and then I would cross all of that out and change the minus 6 to a minus 3 equals the H plus concentration. So we have the hydrogen ion concentration then, H plus equals 5 times 10 to the minus 14 moles per decimeter cubed. Another example of how by including the units it serves as an internal check. You get the expected units. If you don't, you've made a mistake. So we're saying that you've got some 0.2 mole per decimeter cubed sodium hydroxide solution in there. The concentration of H plus ions will be 5 times 10 to the minus 14 moles per decimeter cubed. Now pH, the definition of pH is the log of the H plus ion concentration, but with a sign change, a negative sign there. Okay, so you calculate the log first of all. So the log of 5 times 10 to the minus 14 equals log 5 10 to the minus 14 equals, the calculator tells me it's minus 13.3, but we have to change the sign to get the pH, so the pH would be 13.3, which is what you would expect for a strong alkali.